So let's evaluate continuity of functions. We're going to try to do this without graphing them. So part of this is going to be recognizing what type of function we have. So with this first one, this is a rational function, which makes me think, okay, maybe infinity is coming up where we have a vertical asymptote. But also what can happen with these is where we have a hole show up. And to know whether or not we have a hole, what would be best to do is to factor everything. So we already know we have an issue because when we have x equals 2, well, we can't plug in 2. So something, I already kind of know we have a discontinuity, but just to prove that it's a hole and not an asymptote, then what we're going to have is in the numerator, if I factor with difference of squares, so x plus 2, x minus 2, this is showing me that because the x minus 2 cancels out, that's telling me we do have a hole in the function. And we have a hole at x equals 2, so where we're trying to evaluate it, and also we're not defined elsewhere. So this right here is a removable discontinuity. Discontinuity. And what we would have is this graph of just x plus 2. So we'd have a line. It's just when we're at x equals positive 2, we would have a hole showing up. So it's graphing something like this, where that hole is at exactly x equals 2, making it discontinuous. Okay, with piecewise functions, so where I have functions defined over different domains, what I want to be careful of is the jump, and if there's a jump. And to know whether or not there is a jump discontinuity with these, we're going to evaluate where they change domains. So that's happening at x equals 3 here. I want to see what's the function output this first function's going to, what's the function output the second function's going to. If they match up, we'd actually have something continuous. But if they don't match up, that creates the jump. So what I'm going to do is go to the negative x squared plus 4 and plug in 3. So that's a negative 9 plus 4, so that'll be a negative 5. And I'm going to do the same with a 4x minus 8. So I'm going to have 4 times 3 minus 8, so 12 minus 8, which is 4. So what that's telling me is part of my function is going, nope, it's going down to a negative 5, so maybe something like this. And then up at positive 4, switching those around, that's defined there, and then jump something like that. So this is creating a jump discontinuity at x equals 3. Now, if they had come out to be equal to each other, if we had the same y value, what that would do is something like this. We would still be switching over our functions from something quadratic to something linear, but if they match up, it becomes something continuous. But with this case, it's not. We had something more like that. Okay, piecewise again, but what we want to be careful of is, are they matching up? And with this one, what's actually going to be happening is this is undefined at x. So what we could do is graph this, but what we're going to be seeing here is with this, we're undefined right there. And what I want to know is if this fills the gap that's occurring there. So, you know what, let's get a graph, because this is a little trickier. What I would want to see is whether or not these match up with each other. Does one fill things in? So let's get a graph going. So I'm going to double check. I'm in radians, and we're looking at sine of x over x. So I'm seeing is something that's getting closer and closer to 1, but is undefined at x equals 0. So if we have a coordinate with an output of 1 right there when x is equal to 0, that's perfect. So what's happening here is with this graph, we have our function does something like this, where there's a hole at 1. So that's right at 1, and x equals 0. But the second piece is saying our function output is 1 if x equals 0. And what that piece does is it plugs the hole. It says, actually, we have a coordinate there. So when I'm graphing those two pieces together, I could graph it all at once without picking up my pencil. So that makes it continuous. If we had sine of x over x on its own, that would be discontinuous with a removable discontinuity. But because this is piecewise and we have this value that kind of fills in that spot, it makes it continuous. All right, let's look at some scenarios where we can make a function continuous. So this first case, we have a piecewise function. So we have this negative x plus 3 squared plus 5 for x values less than 2. So that's what's showing up over here. And then what I can see here is we're going to have a linear function, the negative 1/3 x plus c. And what we want to do is figure out what value of c is going to make this continuous. So the idea being we want to graph something linear, and to do that, we want it to match up here, and that'll make it continuous. If it shows up down here, that's going to make a jump discontinuity, which is not what we want. So what we want to do is, at this point, we want to see where does the quadratic equal that linear function. So, zooming around, what I'm going to need is for that negative x plus 3 squared plus 5, I need to see where our output is. And from our graph, we could see that's positive 4, but you could also evaluate by plugging in the negative 2. So we're getting a positive 4. So what we want to see is having an output of positive 4, where does that occur for this negative 1/3 x plus c? But we want to specifically do this when we have x equals negative 2. So what we're seeing is for the quadratic part of our function, let's do this. Right now we have an open circle there at negative 2, positive 4. And to fill that in, that means we need the coordinate negative 2, positive 4 to be part of our second function as well, so that they match up. Okay, so that is 4 equals, and that's a positive 2/3 plus c. So c is going to be equal to 4 minus 2/3. So a 12/3 minus 2/3. So that's going to be a 10/3. So we need c equals 10/3 to make that happen. So just to see, let's see, 3, 6, 9. Here's 10/3. And then we're going down over 3, down and over 3. And that should make it line up perfectly right there. And then we have our linear equation. Okay, so it came down to what coordinate do we want them to match up at, and then having our functions equal each other at that point to solve for c. That would make it work. Let's do that again. So in this case, and we're not going to have a graph here, but if we plug in negative 5, our function is going to be undefined. But with this one, we could actually get an idea of where we're landing. Let's take that 2x plus 10 over 3x plus 5 and see where, or sorry, 15. And let's see, we have 2 times x plus 5 over 3 times x plus 5. So we're creating a hole in this graph. And the hole is occurring at negative 5 2/3. So when I simplified that, it came down to just an output of 2/3. So we didn't have to plug anything in. This is graphing just a horizontal line at 2/3. It's just we have a hole when we plug in x equals negative 5. So if I wanted to fill in that hole, I need the coordinate -5 2/3. And with this one, we're just having the constant. So we need c equals 2/3 to fill that in. Like we saw with that sine of x over x, we just need that constant value to have that coordinate -5 2/3 to fill in the blank. Okay, a few more examples here. So here's some limits that can come up and what it means in terms of our graph. So if we're evaluating the limit as x approaches a from the left or right, and that limit is equal to positive or negative infinity, that's a case where we're getting a vertical asymptote out. Because that would mean at x equals a, we're either going to positive infinity or negative infinity, and they could be matching up, but that's going to mean we have a vertical asymptote when an infinity pops up in the middle of our graph. Let's say we're looking at the limit as x approaches positive infinity or negative infinity, and our function's approaching L. So with this case, it would be the idea of going out to x equals positive infinity or negative infinity, and we're approaching a value in the long run, we're approaching an output. That's going to come through as a horizontal asymptote. So maybe something like this, or we're approaching that value in the long run. So that's going to be a horizontal asymptote as x approaches positive or negative infinity. And that horizontal asymptote is going to be y equals L. That'll be our horizontal line. Okay, so with that, let's see if we can put a sketch together, given some information, and putting it all together. So, just going to do a read through here. So we have discontinuities at -3, 2, and 5. And in fact, maybe I'll go ahead and just kind of highlight, okay, here's where -3 is. So I'm either going to have a hole or a jump, or maybe a vertical asymptote. There's some possibilities. So -3, +2, and +5. Okay, so something's going to happen there in terms of discontinuities. The only x-intercept occurs at +2. So, x-intercept at +2, so I know I have a defined coordinate right there. That's telling me we're probably going to have a jump, or it could be a removable discontinuity, but having that coordinate graphed, we're done with that one. The limit as x approaches -3 is equal to negative infinity. So what that tells me is at -3, and this is the two-sided limit, we're going down to negative infinity on both sides. So that's telling me at -3, we're going to have a vertical asymptote. So that takes care of the type of discontinuity we have right there. And then in terms of graphing a function, I'm going to make this a little nicer. I know we're going off to negative infinity on both sides. We'll see where we go from there, but I know I have that happening on either side of -3. So that actually takes care of that one. And we found our discontinuity at x equals -3. The limit as x approaches negative infinity is -1. So x approaching negative infinity, this is the idea of a horizontal asymptote. So with that, we're going to have a horizontal asymptote of y equals -1. So we're going to have a horizontal asymptote. And what that kind of tells me is, I don't think I have anything going on with x less than -3. Yeah, so we're seeing something like this over here on the left-hand side. So as x goes to negative infinity, we're approaching -1. Okay, as x approaches 2 from the left-hand side, the limit's going to be 0. So that sounds like we're coming out of that coordinate, and that could be a few different ways, so maybe we don't want to draw too much there. Well, except we have to be down here. So I'm thinking we might be going like that. In here, we can cross the horizontal asymptote. That's no issue. I know we're not going up and down because this is our only spot where we're crossing the x-axis. So I'm thinking those will have to connect. And then approaching 2 from the right-hand side, our limit is 3. So what that's telling me is we're up at positive 3 for x equals 2 as well. We can't have another solid coordinate, so this should be an open circle. So there we are at positive 3, and we're going to have a jump there. So we know we have a jump discontinuity at x equals 2. I have a feeling over here we're going like this. Ooh, that got a little wild there, but we're good. Okay, and okay, that takes care of that one. We know we're up at 3. Still have a little more to do there. The slope is constantly 0 on 2 to 5 and 5 to infinity. So what that tells me is that we're graphing horizontal lines. So 2 to 5, which we know we're at 3, so I'm going to have a flat line at positive 3 until I get to 5. I'm not going to draw my circle yet because I don't know where it is. I also know we have the coordinate 5, negative 4. So when we're at x equals positive 5, we're graphing negative 4. So actually, now we know we have a solid circle there, so we have to have an open circle up there. And we're going 5 to infinity is a flat line. So we're doing this. And then we can see our jump discontinuity there. Okay, so just to summarize, I just kind of go through, make notes to myself. I'm going to make sure, okay, at negative 3 we have a discontinuity, which I see my infinite discontinuity there. At 2 we have a jump. At 5 we have a jump. And those are our discontinuities. The only x-intercept occurs at 2, so that's the only spot I'm crossing the x-axis, so that's good. As x approaches negative 3 from both sides, we're going off to negative infinity. As x approaches negative infinity, we're getting closer and closer to negative 1. As x approaches 2 from the left-hand side, we're getting closer to 0. As x approaches 2 from the right-hand side, we're getting closer to 3. The slope is constantly 0 on 2 to 5, and then we're using parentheses there, so those circles are working out for us. And then from 5, and including 5, so we have our solid circle off to infinity. And then we have that at 5, our function's defined down at negative 4. Lots of pieces there to put together the graph, but that should fulfill it all.